Professor Cole is a native of Catalonia and did his first degree in Spain. He did his PhD at Emory University in the United States and has held university positions in England, Liverpool, in Germany, in Leipzig, and is now a professor at St Andrews University. He's a member of the British Academy and is very well known as an authority on cognition in higher primates.
Thank you. Thank you very much, John. It's a great honor to be here today speaking to you. I want to start also thanking John for the invitation and also the collaborators in the work that I will present to you today. This is some of the latest work that I have done. Some of the pictures and names are here for the latest work. Of the earlier work, I don't have them in this slide. Okay, so this is Chrysippus. Chrysippus was a Stoic logician that was one of the first scholars in the Western tradition to wonder about whether animals were capable of reason. He did so by posing the following thought experiment. So imagine there is this dog that is chasing a rabbit. And then the rabbit gets out of sight and the dog reaches this fork path. And the dog has to decide, where did the rabbit go? Chrysippus tells us the dog first goes into one of the paths, it sniffs the ground, it picks up no scent, and then it goes to the second path and it does the same thing, and it picks up, once again, no scent. What it does next is that instead of sniffing on the ground, it runs directly through the third path. The question that Chrysippus had for his dog is the dog capable of logical inference? The fact that the dog did not stop to smell the third path doesn't mean that the dog knows that the rabbit went through the third path. That is the question that he posed. Now, dogs are still philosophers' preferred model species, as you can see in this cartoon. So this is a philosopher and a dog at a cocktail party. So the philosopher is thinking, do dogs think? And the dog is thinking, does philosophy bite? Today I will not talk to philosophers about dogs. What I will do is I will start with Chrysippus' question to try to get at two other questions that I think lie at the core of his thought experiment. The first question is, can non-human animals entertain possibilities? And the second one is, do non-human animals possess the notion of necessity, logical necessity? Although there are other types of necessity, but let's say logical necessity. The way I would like to do that is by doing the following. So first, I would like to give you two definitions of what I mean by inferential processes and what I mean by modal concepts. Then I will tell you about one task, the 2-cup, 1-item task. Then we'll talk about 3 levels of inferential strength based on this task and others. Then we will focus on risk gambling and quantitative cognition. And then we will move to the area of how animals deal with mutually exclusive possibilities. And then I will present an alternative to what I have been saying up until this point, which is an alternative that Lee and Carey proposed, which is about minimal representations of possibility. And I will have a take-home message. During my presentation, what I want to do is I want to combine the insights from comparative psychology and the insights from developmental psychology. You will see that there is a lot of exchange of ideas and data between these disciplines. So it's a truly transdisciplinary enterprise. In addition, this presentation will be sprinkled with some data on economics, because I will talk about risk and I will talk about uncertainty. And of course, the question that started it all is a philosophical question. So the definitions, very simple definition, simply so that we know what's our playing field today. An inferential process, I'm taking a definition from Sperber and Wilson, is a set of premises that results in a set of conclusions which follow logically from or are at least warranted by the premises. Broad definition, but this is what I mean by inferential processes. And I have this picture of a bridge under construction, because inferences very often think about there is a gap, and then how humans and animals are capable of bridging this gap. This is what inferences do very often. And the second key concept for today is that of modal concepts. And here I took a definition from Leahy and Carey, and they define modal concepts as symbolic, logical concepts that mark representations as necessarily, merely possible, or impossible. So between possibilities and certainties. So let's start with during this talk, I will present you two key tasks. They are insultingly simple. They are very simple tasks. But I think that simple tasks very often can provide really interesting results. So let's start with this one, which is simply the 1 item 2 cups task. And again, this is an individual sees 2 opaque cups, and then the experimenter shows 1 piece of food, and then it hides it in one of these 2 cups. The subject knows that food has been hidden, but it doesn't know where. And now the subject has to choose which cup is baited, because the subjects want the food. But before it does that, the experimenter does one manipulation, which is it opens the empty cup. So the subject doesn't see the food there. The question is, would it, think about Chrysippus dog, would it then go for the other cup? In this task, one can solve this task by forming expectations about where the food might be, but it can also be solved by heuristics. And before we go into inferences, I want to talk a little bit about heuristics. And second, this task allows us to study whether individuals are solving this task, if they solve this task, by using probabilities or by using deterministic representations, probabilistic or deterministic, possibilities or certainties. This task, as I explained, has been done with a number of species. And this is very good for those of us who want to try to reconstruct the evolution of cognition, in this case, the evolution of inference. And you can see primates, different mammals, and different birds have been tested on this task. However, this task has other explanations that are not necessarily inferential in nature. So this is what I meant by the heuristic. So let's talk about one of those explanations. One explanation could simply be, has been proposed before in the literature, is that the individuals simply avoid the cup shown to be empty. So if there are the 2 cups and this one is not there, I reject that cup, I go for the other. Not necessarily, because the subject is expecting to find the food in the other. It simply doesn't want the one that is empty. So this task, just the result of this task, does not guarantee that the subject is using an inference, because, as I will try to show you, expectations are a key ingredient of inferences. In order to try to figure out whether individuals solving this task do something more than simply applying heuristics, we tried the following task. And this is the procedure. And here what we are going to have is 3 cups. And then we are going to cover 2 of the cups with a barrier. And then food is going to be placed in one of these 2 cups. The subject cannot see which one. The subject can see that we are putting a piece of food here but it doesn't know where it's going, in the cup on the left or the cup in the center. Then the barrier is removed. This piece of food now is under an opaque cup, so the subject cannot see it. And then the subject is shown an empty cup in the center. This is counterbalanced. Sometimes the food is placed here, but sometimes it's placed here. And always what we do is always open the cup that is empty. Now, according to the avoiding the empty cup explanation, here an empty cup has been shown, but now instead of one alternative, there are two. And the subject has to decide which one is the correct one. So that explanation, as it was formulated, here doesn't work anymore. It cannot explain the results. And subjects can make one of these three choices. They can choose the baited, the correct cup, or they can choose the alternative hidden. So the alternative hidden is this one that was here, but now it's been shown to be empty. Or they can choose the alternative that was visible the whole time. Okay. In this task, we use two conditions. In one condition is what you see here. This is the experimental condition. But there was another condition that was the control condition where this cup was not lifted. Okay. So the individual has no information about the state of this cup. And these are the results for the three alternatives that I mentioned. And what you see here, the interesting comparison from the point of view of the avoid the empty cup hypothesis is this contrast. This is the one that is shown to be empty. And what you can see is subject preferentially go for the cup that is behind, that was behind the barrier, not this cup. So it seems that they are having an expectation of finding the food here. This is also reinforced by the notion that these two cups in the control condition, this one is not shown to be empty, but most of the subject choices are directed to one of these two cups, which again, individuals are expecting to find the food in that location under one of those cups. Now, crucially, the difference between this and this is significant in the experimental condition, but between this and this is not, which means that when they are not given information about which one is the empty cup, they choose randomly between the two cups that were behind the barrier. Expectations are fundamental, as I said earlier, for inference, but not just for inference, for many other processes that individuals engage in, including things like in areas like object permanence, object individuation, and of course, inference by exclusion. This is a very short list. We could list here many, many more other tasks that expectations play a crucial role. But expectations are not of the same type. They also differ depending on whether they are probabilistic in nature or they are deterministic in nature. When subjects solve this kind of task, without additional experiments, we don't know whether the subject is simply reasoning about it is more likely that the food will be in this cup, or is doing something different, which is it cannot be in the other cup. It has to be, it must be in the alternative. This was Chrysippus' question. He was interested about whether animals were able to solve the disjunctive syllogism of the type of the deductive form of the disjunctive syllogism. So here I have this table with different ways in one can solve this task that I showed you. As I already mentioned, one could solve it in a non-inferential way. The data that I showed you with the apes doesn't support this hypothesis. Other animals may be solving it this way. That's definitely possible. And then I distinguish here between three levels of inference, levels of inferential strength, I call them. The first level is the most basic one. And here individuals are forming an expectation. They know that the food is somewhere, but it's simply they know it's somewhere. They are not more specific. In the case of inferential induction, individuals are more specific. And here they can distinguish between which of the cups is more likely to have the reward. Notice that I say is more likely because this level still does not involve certainty, still does not involve necessity. And finally, the inferential deduction, this now is the one that requires that. If this one is empty, the food must be in the other one. It cannot be otherwise. That's the most stringent criteria for the type of inference. Let's look at the data now and see whether we can distinguish this, whether we can find whether animals can do this. These are some of the experiments. It's not an exhaustive list of the different experiments that support and that some of this data. So, to test this idea that in the inferential induction, the form of inference that is based on induction, one thing that is very important and different from the form that is abduction is that the two outcomes between the two cups are connected. The two probabilities are connected. If both are at the same level, but one is decreased, the other one increases. And if this one is increased, this one decreases. But it does not reach the level still of certainty, but they are interconnected. This is a key feature of this level of inference. Can we find any evidence that would suggest that non-human great apes are capable of solving this kind of task? And now I will turn my attention. I told you earlier that we would talk about comparative psychology and we will talk about developmental psychology. I turn my attention to a very nice study by Moody and Carey. And in this study, what they did is they took the task that I presented to you and they transformed it. And they transformed it into, instead of having two cups, they added a second pair of cups. And what they did is, behind the barrier, they had one piece of food. But then in the second set, they do exactly the same thing. So now there are 4 cups, and there is one item in each, sorry, not in each. There is one item in one of these 2 cups and one item in one of these 2 cups. So the probability of finding the food here is 50%. Now, after debating is completed, what they did is they showed that this cup is empty. Now, what this does is an individual that is reasoning by using certainty, it knows that the correct answer is this one. This one is still 50-50. Before it is shown that this one, before it's revealed that this one is empty, this set and this set, the cups in each of these 2 sets have the same probability. So individuals should not show a preference. However, after this one is shown to be empty, then they should change. Then they should show a preference for this one. So that's their task, and they tested 2.5-year-olds until 5-year-olds. And much to their surprise, this task is not easy. 2.5-year-olds have a hard time with this task. In fact, they fail. And even for 3-year-olds and 4-year-olds, they're doing about 60% correct, which is not so high for a task that you might think is not so complex, right? You would think that kids about 4-year-olds, they should be able to solve this task by applying certainty, but apparently it's not what they do. And if you look at also at 5-year-olds, some of them solve it as if they are using certainty, but others don't. So what do the apes do when they are presented with this task? So this is a task that we did with Jan Engelman. And first we tested the reveal NT condition. So let me go back to the human data. And you see the data. So 2.5-year-olds, about 33%, and 3-year-olds, about 60%. We presented exactly the same thing to chimpanzees. And this is what we got. In the reveal empty cup, in the test condition, they got about 50%. They do not pass either. they are choosing once a cup is shown to be empty in one of the sets, then they choose randomly between the two sets. So they do more or less like the 2.5-year-olds and similar to the 3-year-olds. But we did another thing. And the thing that we did is we added a control condition. They did not have a control condition, and what they did is to decide whether they pass or fail, they use the number of cups available to decide what is chance probability of getting it right. So we did that, but on top of that, we presented a control condition. And the control condition was very similar to the test condition, but instead of having two sets of cups and two barriers, so barrier here, food is hidden, barrier here, food is hidden, we had a single barrier. And then one piece is hidden and another piece is hidden. And then after the barrier is removed, the procedure is exactly the same. One cup is shown to be empty, and then they choose. One thing that is important here is because it might be that their choices are influenced by which cup is open. And that is what determines their choices. That's why we had this control condition. In addition, in this study, we added another condition, which is the reveal baited, which we borrowed from Gautam and colleagues. So, and this is a study that we did with children, and what they did is basically the same, exactly the same, the test condition, but instead of showing the empty cup, what they did is they showed the baited cup, and then they removed it. So here, the subject has seen an empty cup. Here, the subject has seen the baited cup, and now that food is gone. Where will they choose? Will they choose this one, or will they go for this set? That's a question that Gautam and colleagues asked. And then to make it parallel, then we added this control condition that mirrors the control condition that we use for the reveal empty condition. You've already seen this data. This is the original Moody and Carey with chimpanzees, showing the 50% correct. And now in the control condition, what we saw is actually, it's much lower. So what that means is chimpanzees are doing something here that they don't do in the control condition. So they are benefiting somehow of the reveal empty condition, something that was not apparent in the Moody and Carey experiment with children, because I repeat, they did not run this condition. And that's why I was saying that using chance is really tricky in this case, because you can use chance by counting how many cups you have, so 3, or you can use chance by saying it's 50-50, because you choose from this set or you choose from that set. So which one is correct? So that's why we ran that control condition, because then we can directly compare what is the chance probability, not the chance probability, what is the actual probability that they would choose the same cup in the two conditions. And in the reveal baited condition, what we found is that when they see that the food is gone, then they increase their responses to the target cups, to the ones that are likely to be baited. And they also do that in the control condition, but less so than in the experimental condition. So what we found in the chimpanzees is that even though the pattern of results in this condition is very similar to the children, especially to the 2.5 and 3-year-olds. And this one is very similar to the 4 and 5.5-year-olds in the Gautam study. What we saw is that when you add the control conditions, the chimpanzees are benefiting from these manipulations. They are being more accurate at finding the food. However, notice that they are not 100%. And in fact, if you looked at the data, this is the individual data. Here you only have 3 subjects that would be classified as they are choosing based on certainty. And here you have nobody. Another task. Looking at the same thing. Looking at what is the effect of removing the food on their choices. Think about what I told you about in the inductive inference. The 2 probabilities in the cups are linked. If one goes up, the other one goes down. So in this task, we presented again 3 cups. And then you can ignore this, it doesn't do anything. So 3 cups, we show them that they are empty. And then we place 2 cups behind a barrier, like the experiment that you saw before. So the beginning is very similar. And then we presented 4 conditions. Within subjects, a 2x2 design. The 4 conditions are these. The cup could be in the center. The baited cup could be the center one or the one on the side. So it could be this one or it could be this one. And then we cross that with, did we lift the cup or not? The cup that we lifted was always the cup in the center. And what happens is, in half of the trials, and the last step is then after we do these manipulations, then we remove the cup in the center. They can never choose it. So what this means is that in half of the trials, they didn't see what was under the cup that was removed. This one and this one. And in the other half of the trials, they saw what was under it. In one case, it was empty, and in the other case, it was baited. So when now they choose here the food is gone, and here the food is still there. If they can reason that if this one is empty and this one is full, there should be no food here in this case, and the food should still be here. Is it clear how it goes? Okay. So these are the results. And let me start by, see, what you have is the number of choices that they made to the cup that was behind the barrier when the baiting took place. That's a correct response, so to speak. And then here you have by the removed cup. Was the removed cup baited or was the removed cup empty? And then the factor is, did they see that or not? Let's start with when they were not shown what the content of the removed cup was. What they do is they choose about 80%, the other cup that was behind the barrier. Okay, that's consistent with the data that I showed you in the very first experiment with the 3 cups. They prefer the cups that are behind the barrier during baiting, because that's where the food went. Now, the interesting part here is, so think about this as a baseline. Now, what happens when they have access to the content of those cups? What happens is when they see what is shown is that the cup that is removed is baited, they decrease their preference for the cup behind that barrier. But when they see that the baited cup, that the cup that is removed is empty, they increase the preference for the cup that is left. This is what I was telling you about, is depending on what is being taken away, if it's empty or is baited, they change their choices. This is consistent with what I showed you earlier with the 4-cup experiment. They seem to be linking these 2 probabilities. One thing I didn't say at the beginning, but I think it's important that I say that, is in all these experiments, we are interested in the spontaneous performance. We are not interested about what happens after they are given hundreds of trials. We want to know the first time they are presented with this task, or the first 10 trials, what do they do? We want to know the spontaneous performance. If you train them hundreds of trials, they could be perfect, but that's not what we are doing here. Let me say, in general, in these kinds of tasks, we rarely, I don't think in these kinds of tasks, ever found an effect of trial number. So they are not learning. The responses that they produce on trial 1 are the same responses that they produce on trial 12. Okay, so let me just get that out of the way. Okay, so it seems that this kind of inference, the inductive inference that is based on likelihood of where the cup, where the food might be still located, is supported by the evidence. But this one, about certainties, is not. Because if I go back one, you see here, this one, it increases a bit, but this is still not the 12%, the 100%. So there is an increase, but it seems that they are not operating based on certainties. I'll give you two other pieces of evidence that go in the same direction about their, as far as we can tell, the current evidence leads us to conclude that they are not operating at the level of certainties. So I'll present you now with two different experiments, not with these cups, but experiments that have to do with risk, gambling, and also I'll talk a little bit about quantitative cognition. So now we're making a leap into a different area, but you will see that the results in that area are consistent with what I just showed you. The first task is one where subjects have to choose between risky and safe options. And that's what I was telling you earlier about economics. So this is some of this work is very relevant for economics. And the subjects have to choose between two options. One option is this yellow cup, and this is what is called the safe option. And food is always there, and it's always the same type of food. So if subjects choose this one, they always get food. Or they can choose from one of these cups, and this food that is under one of the cups is better. The quantity is higher, but it's riskier because only one cup is baited. So subjects can decide, so here, the size of the safe reward, the one that is always put in the left container, and subjects see the experimenter put it there. It's 1/6, 1/3, or 2/3 of the risky reward that will be hidden in one of these cups. Okay, and then subjects have to decide which of the two options they want to go for. Do they want to choose the safe option, yellow cup, or do they want to risk it and go for one of the blue cups? The blue cups, you have here, there are 4 of them depicted, but they vary between 1 and 4. So the probability of getting it right varies. And I'm going to show you this data. This is their choice, the choice of the risky choices, the blue cups, how many times, what percentage they go for the blue cups as a function of the relative reward size. One is the point of indifference. This is between two options that they have exactly the same payoff. In this case, in this particular case, is between, is 3 blue cups with 1 piece of food in one of these 3, or the safe options, or the safe option with a reward that is 1/3 of the size of the one that goes in the blue cups. So in the long run, if an individual chooses the safe option, they will get exactly the same as an individual that in the long run chooses the risky options. So that's the point of indifference. The point in indifference, in theory, subjects should be 50% because it doesn't matter, right? Well, the apes in general, what they do is they are risk prone in this task. They prefer to gamble. They prefer to go for the bigger piece. That is a general finding that you find in this kind of task, that and species vary. Some species tend to go for risky options than others. For instance, chimpanzees tend to be more risk prone than bonobos, for instance. If you want to know why, you can ask me later and I'll be happy to elaborate. But the real reason I'm showing you this graph is because the ones that I have circled here in red are those where the blue cup, it only has one blue cup. Those are the ones where you are certain, if you pick the blue cup, you are certain to get the biggest piece of food. And what you see here is when the small reward, when the reward in the safe cup is small or medium, they are doing quite well. But when the reward in the safe cup is bigger, now they don't choose based on 100%. If they had the ability to think about certainties, they should do that because they cannot lose. There is one cup, one blue cup, and the biggest reward is under that blue cup. But they don't use this. I'll show you another experiment that shows the same thing. Again, different chimpanzees, different setup. And in this case, what the chimpanzees have to do is they have to choose between two trays. And the trays differ in the number of cups under which we're going to hide the reward. So the chimpanzee first sees that this tray has 6 cups and this tray has 2 cups. This is just one example. We have different numbers of cups in different trials. And then after they have seen this, what we do is we lift these occluders and we put some of the cups inside there, and then some of the cups we leave out here, and the chimpanzee sees that we are baiting one, we are baiting another one there, and on this side we are baiting one, and now we put these cups under here, we shuffle them, and these are covered so they cannot see the food from above. We do the same thing here, and now the subject has to choose. So what the subject has to choose is between, you have 6 cups here and 2 cups there. You've seen 2 pieces of food go on this tray. 2 of the 6 cups are baited. In this other tray, 1 of the 2 cups is baited. Can they pick the tray that is more favorable? The tray where they are more likely to get rewarded? Here I am representing to answer that question is, it depends. And it depends on the ratio between the quantities. It depends on here what you have is the probability ratio that we call is basically the probability of the low probability, the option with the lowest probability divided by the option with the highest probability. And as you can see here, when the ratio is 0.2 or 0.3, they are doing quite well, around 80% correct. When the ratio is between 0.7 and 0.8, they are doing much worse. This is 50%. So they are choosing depending, they are sensitive to what is the probabilities that are involved. Now, all the gray diamonds, yes, you can see gray. All the gray diamonds are trials in which one of the trays had a certain option. There was, for instance, only 1 cup. So there you cannot lose. And unlike the previous experiment, the rewards that go on these trays are the same size. Sometimes they vary in number, but in many trials you only have 1 and 1. What varies is the number of cups. What you can see here is that in all of these, if they were operating based on certainty, they should be up here. They should be picking the highest possible because it's 1 cup against 2 in the other option. However, this is not what they are doing. What they are doing is they are using the ratio of the quantities, in this case of the probabilities, to decide what to choose. This is another piece of evidence suggesting that they are not operating on certainties. So that's what I would summarize from this part of the talk. Before I move on to the next topic, I want to mention something about quantitative cognition. And I show you the data on this, but you could look at other data on relative numerousness or intuitive statistics that when you plot their performance, where you plot their accuracy, what you find is something like this. In every case, the ratio of the quantities or the probabilities determines their accuracy. And it fits beautifully with Weber-Fechner's law, the 2 Leipzig-based psychophysicists. So let's go on to the last topic. And this one is about dealing with mutually exclusive possibilities. And here what we're going to do is we're going to switch. We are not going to talk about cups. We're going to leave cups aside. We're going to talk about tubes. Again, a very simple task. And this is something that developmental psychologists, once again, they have investigated in children from the ages of, say, 3 till 7. And they have used tasks to see whether infants and children, in this case children, not infants, children are capable of thinking about future hypotheticals, future possibilities. Their experiments are very heavily, verbal description is very heavy on these experiments. They explain the procedure to the children by giving them instructions, by telling them a story. As you can imagine, we cannot do that with the chimps. We can tell them a story, but they will not know what we are talking about. So we need to find a way to try to ask the same question, but non-verbally. Redshaw and Sudendorf adapted one of those tasks that developmental psychologists had used to ask that question about, are they capable, chimpanzees, of understanding mutually exclusive possibilities? And the task, again, is insultingly simple. And what it involves is you have a tube, and then the experimenter places a piece of food or a toy, and it drops it into this tube. Now, this tube, it has two exits. And what the experimenters measure is whether children and chimpanzees, when the experimenter is about to drop this into the tube, do they block one exit or do they block two? Do they try to guess it's coming this way, or are they conceiving of possibilities? That's according to their reasoning. I'll show you the data, Redshaw's and Sudendorf data. Let me start with the chimp data. The answer for the chimps is no, a resounding no. Over time, they can learn, slowly, but they can learn. But I told you, we are not interested about whether they can learn. Yes, give them 100 trials, 200, they will do fine. We are interested in their spontaneous performance. So they don't do it, they just put one hand. However, 4-year-olds do quite well. On the very first trial, nearly 80% of the 4-year-olds are doing both hands. And here you have the other different ages. You can see that there is a nice developmental progression on these. So big difference between the chimps and the children, especially the 4-year-olds. Now, this task has been criticized. And what I will show you now is some of the new developments on this task. This is not the end of the story. It will be to be continued. But I'll show you the things that have happened since 2016, or some of the things that have happened. The first one is, one criticism of this task is that chimpanzees have a hard time doing things bimanually. That's why they don't do well. Personally, I don't think that's a very good explanation, but let's go with that. So this is something that Lambert and Osbath tried to do. And the way they did it is, they adapted the task by Redshaw and Sudendorf, not in this paper, but in a subsequent paper. And in that subsequent paper, they used 2 vertical tubes. There was no fork, there was not the Y-shaped tube, just 2 vertical tubes. And what they did is they show a piece of food, and then the chimp doesn't know where it's going to come. They still can do that, because you could think that maybe the Y-shaped tube is difficult to understand. Okay, so 2 vertical tubes. When the chimp doesn't know where it's going to come out, the results were the same. It did not matter whether you have a Y-shaped tube or you have 2 totally independent straight tubes. But then Lambert and Osbath did another thing that Redshaw and Sudendorf didn't. And is they had a condition in which the chimp would be certain that food would come out from both. And the way they did that is they had the 2 vertical tubes. They had 2 pieces of food, and they show it to the egg that they were about to drop 2 pieces of food. Now the egg should put both hands, right? If they don't put both hands, there is something really wrong with this task, they argued. This is the first trial, and I highlighted the certain condition. They did the certain and the uncertain, but for our purposes, the certain is the important one. As you can see here, on the very first trial, no chimpanzee could do this. On top of that, if you look at how long it took them to pass the task, you can see some never passed. The one that was the earliest to pass was 6 or 7, trial 6, trial 7. So it took a long time. Once again, this is strange, would you think, because 2 pieces of food are going down, so what's going on? Then Engelman and colleagues did a different thing. They removed the tubes. Forget about the tubes. The tubes, for some reason, may be difficult to understand because there is also in the developmental literature and also in the comparative literature, there's the issue about the gravity bias. The gravity bias sometimes creates serious complications in terms of interpreting certain results. So get rid completely of the tubes. And what they did is they presented chimpanzees with a task in which they had to pull from boxes that were either transparent and they could see the food, or boxes that were opaque and they could not see the food. And the question is, would they pull from one rope or from two ropes? In the transparent, you can just pull from one because you see where the food is, right? But in the opaque, well, it could be in one or it could be in the other. The results, and these are the results of two different experiments measuring the same thing, tested in different ways. This drawing corresponds to this data. And what you can see here is that in the condition that is transparent, you see that the two ropes are pulled in the opaque condition much more often than in the transparent condition. So an ABA design, and you can see that, yeah, this is quite convincing. They tested the same idea with a different setup, also pulling ropes. The results were very similar. This challenges the results of Recho and Sudendorf, because why would a chimp pull for both boxes? Now, there is a key difference between Recho and Sudendorf's experiment and Engelmann and colleagues, is that there is a difference between what is being called external uncertainty and internal uncertainty, or physical uncertainty and epistemic uncertainty. In this case, physical uncertainty is when something has not occurred yet. When the Recho and Sudendorf are about to drop it, but they have not done it yet, the event has not occurred. It's still in the future. This is what it's known as physical uncertainty. When the thing has already been dropped, that is, the event has already happened, this is in the boxes, and now the subject has to decide. The reason this distinction is important is because children find one easier than the other, and for adults, it's the opposite. So apparently they are not equivalent. So what we did is we tried, so this one is about epistemic uncertainty. Recho and Sudendorf is about physical uncertainty. So maybe that's why they are different. The results are different. So we tried the task now with physical uncertainty. And the way we did it is instead of dropping food, we went back to their Y-shaped tube, and we presented two conditions, one with a Y-shaped tube and another one with a straight tube, and then we had two trays. But instead of dropping food, what we did is we dropped the stone. What this stone did is if it hit the tray, it knocked down the tray and they didn't get the food. Okay? So it's not about dropping the food, it's about dropping a stone. And what we wanted to know is whether chimpanzees would try to stabilize both trays here, but only one here. We were careful to follow all the presentation and trials before we reached to the test. We did it like Recho and Sudendorf have done. The only thing that we changed is whether instead of dropping the food, we just dropped the stone on trays that both contain the same amount of food. And what we found is that in the single tube condition, they tend to stabilize one 50-50, but in the Y-shaped tube condition, they tend to stabilize both. There is a significant difference. Now, once again, notice that they are not doing 100%. Once again. And okay. Okay, and what I have left, I want to address one explanation that has been made for the data for children and non-human animals, which is that the idea is that these groups, Leahy and Carey, argue they may not have modal representations of possibility, some of these data could be explained by a minimal representation of possibility. And the way the reasoning goes is, say, presented with the tube task, but this can be translated to the cups. In their idea is that under this minimal representation of possibility explanation, what individuals do is they decide that's where the food is going to come out. So they are representing the possibilities as facts. They make a guess and they say that's the one that's going to come out. While in this other possibility is individuals represent possibilities as possibilities. If we could ask them, they could say, yes, I can choose this, but I know that it could be the other one. But you see, we cannot ask this question. There is already some data in the literature that challenges this. And one of the pieces of data I already showed you is the one where you had the cups and you see that their responses, their accuracy are ratio dependent. That ratio dependency cannot be explained by the minimal representation of possibility. I'll show you another piece of data and we'll finish with that. I'll show you now a test, again, from economics. And this is a test on post-decision wagering. And we are going back to the cups. This is work that Ben Jones is doing at the moment. And here, the subject is shown 2 cups. Food goes under one of them, and there are 2 conditions. In one condition, the subject, in the certain condition, the subject sees where the food goes. So it sees that we place the food there. In the uncertain condition, the subject knows that the food has gone in one of the cups, but they don't know where it's gone. Okay. And then after subjects make a choice, they have decided which one they want. Then we offer them half a grape. So you have the 2 cups, they make a choice, and after they have chosen, we pull it back, and now we let them choose again, but we offer them a half a grape. Would you want to ignore what you'd done earlier and go for half a grape? The question here is, will the participants take this half a grape when offered a choice between it and the still unknown contents of their chosen cup? If our reading of Leahy and Carey is correct, their minimal representation explanation, there is no reason why subjects should change. If they decided the food is on the left, they should stick with it because there is one grape, one whole grape, not just half. This is the results that we found. Not surprisingly, in the certain condition, when they have seen the food go there, they rarely go for the half grape. But in the uncertain condition, in about 40% of the trials, they go for the half grape. If they were treating possibility as a fact, why would they forego a full grape for half? This is just to show you that all species show a similar pattern. Bonobos, chimpanzees, gorillas, orangutans. I have another experiment, but what I will do, I'll skip it because it gives similar results to what you have already seen, which is when now you use the same task, but now you show them what you remove. Now they know whether the cup that has been removed is empty or not. They change their choices are different. So they are taking into account what is the food that has been removed. So, but that's, you've already seen data like that. Okay. The 2 questions that we started with, initially triggered by Chrysippus thought experiment. Let me start with the second one. Do non-human animals possess the notion of logical necessity? So far, with the evidence that we have today, I would say, no, we don't have good evidence that they operate based on logical necessity. So, by the way, Chrysippus also, in his writing, he went for that alternative. So apparently, even without doing experiments, Chrysippus was right. So he thought that the dog would not operate based on this disjunctive syllogism, the full-blown deductive inference. The first question, can non-human animals entertain possibilities? I'm taking a license here because I only show you apes. I talk about animals. Other animals should be tested on this. Let me tell you about the apes. Here, the answer is trickier. It's not as clear. I think that there is some evidence that they may consider possibilities because the data that I showed you on them pulling from the two ropes or stabilizing the two platforms or taking into account what is being removed when deciding what is the choice, when determining or changing the choice that they would make otherwise. This is just an elaboration on the same thing. So I would say if I had to summarize this data, I would say the great apes are capable of abductive and inductive inferences. This is the weakest forms of inference, but there is no evidence of deductive inferences. The great apes' reasoning seems to be probabilistic and not deterministic. And although the initial results suggested that apes were incapable of anticipating potential future outcomes, there is now some data contradicting this notion. Still, this evidence for anticipating possibilities is probabilistic in nature. They are not doing certainties. Okay? So that's all I had to say. So thank you very much for your attention, and I'll be happy to take questions.
Many thanks for leading us into that wonderful world, animal logic. We normally have a little break at this time to let people who need to go to. So, questions for Professor Carl?
Yes.
Tristan.
So there's a lot of work in the ecological settings with many of these monkeys, and of course it's difficult to make experiments, but at the same time there's like a trillion observations, right? I mean, the biologists in the field sleeping there and videoing, and so can we get any complementary inferences about these ideas from the field work?
I can give you a reason for why I think this ability has evolved. I will do that. But before I do that, I will answer your question. It's hard to know in the field this kind of, get answers to these questions because you don't know the history of the individual with their natural, with the problems that they face. Many processes may be involved in them finding those solutions. And when the researcher gets there, it's too late. We never have, is the very first trial. We never have it. So that's what I would say. Now, what I can tell you is about why this ability may have evolved. So one could think, well, I understand why animals have evolved the ability to quantify, to decide between richer and poorer food patches. But why should they do something that has to do with something that we would call probabilities? So I have a slide for that. Okay, so there. Okay, so imagine this chimpanzee has to decide between these two food patches. Well, probably would go for the one on the left. It's richer. They are at the same distance. So, but now, what happens if there are also 3 other individuals going for that food patch? All of a sudden, the richer patch might be actually not the most profitable because these competitors are going to take away some of this. And this could be a reason why not only the great apes, and I bet this applies to other species, have evolved an ability to deal with quantities, but also something that we could call conditional quantities. It's not just about the quantities, but also what other factors play into their decisions beyond just the actual quantities. Can we do these experiments in the field? Once again, no, because from basic observations, we get there too late. What people have done in the field is to present patches of different richness and vary the probabilities and then see how monkeys respond. And that can be done, but you need experiments. Just the observations, I don't think, are enough. Don't get me wrong, please. I think the observations are extremely valuable. I think the reason why we do these experiments is precisely because we observe them do stuff. And then we wonder about what's the cognitive mechanism underlying this really interesting behavior. Okay.
John Tonkin.
This is a very generic question from somebody who works in a very different field, and I'm sure you get asked it all the time, in which case I apologise for boring you. So I don't work in this area, but if I did, I would definitely be starting from a very different place. I would not expect generic answers to questions of the sort that you're posing, which apply across all situations. Instead, I would think, in any situation, the animal's got some model of the world. It could be more complex, it could be less complex, but it's going to be very situation specific, and how the animal uses it is going to depend on all sorts of things as well.
Yeah.
And what you're really doing in that case is figuring out about the animal's model and use of that model for this particular situation rather than answering a general question.
Yes.
Is that something that comes up all the time? I feel it probably does.
No, it doesn't. But I see the point you make. But let me say something is, even when you try very different preparations, sometimes you get things like Weber's law popping up everywhere. So there is some mechanisms that seem to be, that cut across problems. I agree with you that you change the conditions of the task and you may get something different. Yes. But sometimes we change those conditions and the same thing keeps coming back. So without disputing what you are saying, I would counter that by saying, in some cases, you find these generalities.
Greg, and
Thank you. Very interesting talk.
Thank you.
I was just thinking about tubes and my understanding of tubes and how that might emerge from experience. And I was thinking, so this might be a less sophisticated version of John's question, but it's the ability to sort of actively interact with a tube, stick pebbles down it and see them go down it. And I'm wondering, have you sort of tried playing around with transparent tubes and things so they can see these internal workings?
This is something that people have suggested. Some of the authors have suggested. As far as I know, it's not been done. What I would predict, they would be very good there, because they would track where the food is going, and immediately they would see both falling, they would put their hands.
Certainly, sorry, just if I may. What I meant was so that they understand when they get to the opaque tube task, they understand tubes and how stones work their way down.
Okay, good. So you're talking about the Y-shaped tube. Sorry. Yes. As far as I know, it's not been done. What I would say is, if I were to do this task, like you're suggesting, one thing I would do is I would change from vertical to horizontal, because the gravity bias can create very serious difficulties. So I would put them on a horizontal plane and then drop the thing, let it roll, and see whether that changes. It might. Yeah. And it goes back to your question. With that new setup, you may uncover an ability that it was not there before. I mean, or at least you could not detect. Yes.
My question is actually related to the very first question, which is, I was wondering, when you showed the data between the children and the animals, I was wondering if it doesn't have to do more with the setup that the experiment is just kind of strange for animals, and since you're only looking at the very first few trials, maybe they just need more time to adjust to kind of this play setup.
Yeah.
And children might just find that easier. So I was wondering how that might confound it.
It is possible. What I would want to have then is a condition that would control for that. That would control for some form, for instance, some form of heuristic or some form of associative learning that doesn't have the key elements of the task, and then subtract that from the learning curve that one observes. Again, this has been done in other studies. As far as I know, it's not been done in this kind of study. But yes, I mean, sometimes I think in my field, sometimes we run the risk that we say, well, if they learn, it's not interesting, nothing's going on. And I think that's an oversimplification. I think that comes from an over-reliance on first trial. It might be that something really interesting is going on that is not, say, as heuristic-based or associative-based as one may think. But to do that, then you need a condition that is as similar as possible to your experimental condition, but is missing that key ingredient. That's easier said than done. Okay. Deborah.
So just following up on the same question, is it simply that as we grow up, we understand a social nature of a particular setup, we understand what you're kind of trying to do, the rules of the game, because why would an animal expect that what it sees would actually pay off veridically? Why not, as in this example, just try out different things at different times? So say, for example, in the very last slide you showed, even in the certain condition, there were a few trials that they did the other thing. It wasn't 100% that they didn't. So is it something about just as children grow up, they are exposed to the idea that there is a binary yes or no in the world, like a cultural construct that we invented, and they just start playing into this?
Yeah, that's a very interesting question and a very difficult one. And some people would say language is what does that. Language allows you to have a symbolic marker that allows you to make this concept crystal clear. Without that, it's much harder to get that certainty. That's one explanation. Another explanation is, no, language simply latches onto something that is already there. Which one is right? I do not know. But for sure, experience growing up and seeing these kinds of things is going to have an impact on the way they respond. We don't know it for the tubes, but we know it for tool use, for instance. If they are exposed to tools, if they can play with tools before you present them with a problem-solving task, they're going to do better. But then the interesting question then becomes is not that they do better, but is what is the mechanism that they've been able to develop or use to be able to perform better. Yeah, you had a follow-up question.
It's a really, really interesting answer. No, thank you. I'm really excited that you pointed that out. And I was just wondering if you see with children growing, whether that ability emerges together with a language ability or perhaps with exposure to a particular cultural context.
This is the 1 million pound question. And you're going to have people that are subscribers of language is what makes us smart. And you will have people that will say, no, because we are smart, we can do language. You can find arguments for both camps. I personally, if I may give my personal opinion, is I think language cannot bootstrap itself from nothing. It needs to be grounded on some basic cognitive abilities. It's not, it seems to me sometimes, sorry, some of you are the language proponents. I'm not trying to oversimplify the position, but quite often it seems to me language is the silver bullet, is what will solve all our questions. And I think that's maybe going a bit too far.
Thank you for an amazing talk, and I'm sorry if the question is too naive. They are genius, the setups, and I understand that you are not looking at the learning. But related to the previous questions, is there any chance, or do you consider at all any possibility given that in some of the cases we almost characterize it as gambling, as them tending to gamble instead, and it sounds slightly strange. Do you take into consideration any instinctive behavior to actually choose something or another, and also the difference that would be on the field, given that this, is there any chance they consider this play, or is there real necessity to choose something?
Let me say two things to your question. I mentioned in my talk that some species are more prone to make risky choices. There's been some debate in the literature about what is the reason for that. And one of the explanations that has been given, I don't think is 100% perfect, but it has to do with the feeding ecology of the species. Some species have been selected to feed on resources that are patchy. They are high quality but patchy. If you don't eat those resources, you die. Therefore, you need to be risky. You need to take risky choices. You cannot just stay put and feed on low quality resources. Other species have been selected to feed on those low quality resources. And those, some data suggest, that are the ones that are less risk prone. So you could see a connection between what is the feeding ecology studied by, say, field primatologists, and how it translates into this task. But we have to be, I think, very cautious, because this is it's a nice story, but let's be very aware that it's a story, because there is a long distance between what they do in a lab with 2 cups and a table and what they eat in the wild. For one thing, that's ignoring the ontogeny of these individuals, the ones in the field and the ones in the lab. And this might be an oversimplification. However, in the quest to try to find evolutionary explanations grounded in socioecology, this is one thing that has been argued. Second point about the gambling. Okay. The tasks I showed you perhaps are not very convincing in terms of gambling. I'll give you another example, another task that we have used. And you tell me whether it's more convincing to you. Maybe not, and that's fine. The task begins by the experimenter giving a cookie to the ape. And we have 3 sizes of cookies: large cookies, medium-sized cookies, and small cookies. And the experimenter gives a medium-sized cookie. If the orangutan returns it, then it may get something better, but it may get something worse. There are 6 options there presented to the ape. And if it returns a medium-sized cookie, imagine that you have 4 large cookies and 2 small ones. If the ape has a medium-sized cookie, it could simply eat it and be done with it and go to the next trial. Or it can return this cookie, so incur a cost for a chance to get one of those 6. Would you think that that's more similar to gambling? Because there is a cost involved. There is something I may lose. Would you say so?
I would, but then you would also have to control learning, or gambling is addictive to humans.
Okay.
So then you could have that problem.
Good. The issue of learning is easy, because you can look at what they do in trial 1, what they do in trial 2, and then see whether their preferences change. Another thing you can do is you can present different trials where the composition of large cookies, medium-sized cookies, or small cookies varies. Imagine you can have some that are that you can never lose, because you may have 4 large cookies and 2 medium ones. So if you're giving a medium one, you should always gamble, because you can never lose. The worst thing that can happen to you is that you get a medium-sized cookie. In other cases, you should never gamble, because you may have 6 small cookies, and in that case, you should never do it. When you look at what is the responses, and I mean, we did something like 18 different combinations between large, small, etc. The subjects are pretty good at deciding when is a good idea to gamble, because they are adjusting the likelihood of returning the medium-sized cookie to the probability of winning something better. They are not perfect, they are not, but you can see clearly that they are sensitive to those. And this again is not surprising. It's exciting, but not surprising. If you think about what I showed you today, about their ability to decide which one of these two trays I have a better chance of getting the food. Okay, sorry, long answer.
Could I follow on from
Yeah.
that to ask you about intraspecific
Yeah.
variations?
Yes.
Slightly put into my mind by this. Do you know about the wonderful polymorphism, single gene polymorphism in Drosophila between sitters and rovers?
No, I don't.
It's wonderful. It's a single gene, and some Drosophila, having found food, will stick with it, limited under conditions of limited resource.
Yeah.
And others, called rovers, will go off in search of better fields. And it's a balanced polymorphism that's maintained in the population, because if you're a sitter and the rovers are dominant in the population, you'll be in an advantage when food is rare, and conversely. Now, with apes, you have limited numbers of animals necessarily. You can understand that. But I wonder if there is any variation. This polymorphism is said to exist in our species too, with the homologous gene. There was a PNAS paper about this. I don't fully believe it, but it is claimed that the homologous gene produces people.
We don't have the data with apes, as you guessed, because our samples, two main problems. One, our samples are very small, and second, we cannot do crossbreeding. We cannot selectively breed those that show the trait. So that reduces our ability to identify those polymorphisms. However, there is work done with rhesus monkeys, because rhesus you can have many more, and people have tried to look at whether they can find some indicators that there are some some individuals that are particularly prone to those. I know that people have been trying, but again, you would need lots of macaques to be able to do this. So as far as I know, I don't think that we have an answer for that. I would be very interested also with what you said about what about the role of ontogeny? Would a certain genotype, for Drosophila may not work, but for another species that is exposed to outcomes of risky choices that are always favorable. So similar to what would be in economics a hot hen effect. So anything that this individual does, no matter how risky it is, it always wins. Would then those individuals be more prone to take risky choices? And would this have an effect perhaps on gene expression? Could one detect those effects at that level? I think that's absolutely fascinating. But when it comes to primates, I don't think that we have those answers.
So thanks for the talk, it's very interesting.
Thank you.
I was thinking about some of the experiments with the cups, and right at the beginning, it reminded me of some of those trick questions where there's this assumption, you assume that there's just one ball or one bit of food because you saw it being put there, but then the trick is that there's actually already food in one of the others. I was wondering about if any of the experiments address that or this growing assumption.
Okay, very good. I'll give you an answer, and we never trick them. We never do tricky things because
Yes.
then it
Yeah.
could. So that's the
Absolutely.
first thing.
Yeah.
But notice that in some of the experiments I show you, we show the empty cups at the very beginning.
All of them.
All of them.
Okay.
See, there is nothing there.
Yeah.
Then you put them down.
Yeah.
You put a barrier,
Right.
and now you show the food, and it goes in.
Okay.
So, could they think, well, there is a trick somehow? Yes, perhaps they could. Now, I don't think they have a reason to believe that because of us, because we've never tricked them in this way.
I just want a quick clarification of that. So not that they could think that there's a trick, but I was thinking more about learning or that assumption, which often sometimes comes a bit possibly with education, is the idea that you have this clear understanding that I can rule out any other possibilities, and this is the same logic as the experimenter has. So I think quite close to what you were saying. So as a matter of procedure, they usually see that all the cups are empty, and then the whole thing is set up.
Yep.
Okay.
Yep.
This may also be a naive question, but do you control for the sort of social reward knowledge of the monkey to the experimenter? Like, is it someone that they often get reward from, or have never ever gotten reward from? And might that change things?
We work with the same subjects multiple times. Also, there are multiple experimenters, and there are also apes in different locations. Sometimes, yes, you work with the same experimenter for a number of studies, but sometimes they win, sometimes they lose. And new experimenters comes in and they run studies. So I don't think they automatically associate reward with the experimenter, because in some of the tasks they fail miserably. If they don't pass, they don't pass.
Okay.
Yeah. Does that answer your question?
I think so, yeah.
Well, I'm just wondering, coming back to the cookie study,
Yep.
you said they can gamble, they can do it pretty well. How well humans can do it?
Oh, we have not done this with humans.
I'm just wondering, I mean, it's a task where everyone can imagine themselves just trying to gamble. So what humans would do in this situation?
If you have enough cookies, we could play this game later on. How many subjects we have? I assume that humans would do well.
I mean, how much better than apes, or just I'm
It's
just
an
wondering,
empirical
just
question.
wondering.
It's an empirical question.
Yeah.
I do not know. I can show you the data if you want to see it, to see how good they are. Would you like to see it? I'll try to find it. Let's see.
While Professor Cal is looking for these data, can I ask how many people would like to join us for a drink afterwards? Because I'm just choosing where we might go. Can you put your hand up if you come and have a drink with us? Anyone? 1, 2, 3. Tristan?
I have to go change. Come back.
So three of us. I think we'll go to the Eagle, which happens to be on the route. All bar one is getting rather unpleasant. So anyone who fancies a drink, even if you didn't put your hand up, come and join us in the Eagle and the Department of Bioethics. Now.
Okay, so I can see it here. Can I stop it? Okay, so let me start the video again and I'll. Okay. Let's stop. Okay, let me try again. So these are the 6 options. She's given a medium size and now she receives a smaller one. So there she lost. Okay, so that's the way it works. Medium size goes to the orangutan in this case. The orangutan can see the 6 options. And then once it returns it, the experimenter gives 1. It's predetermined, okay? So before the experiment. And so these are the species tested, and these are all the different combinations. So you see, some of them you can never lose, you should always gamble there. Some of them you should never gamble because you will lose. And anything in between. And okay, so this is one experiment. You see some species are better than others. You have long-tailed macaques. Our sample sizes are very tiny. So I would not make a big deal out of this on the species differences. Macaques are always gambling. Only when things get really bad, they start to not gamble. Capuchins are better. This is, by the way, this is the probability of something getting better. So above 50%, 33, 17, 0. And you can see that, yeah, they're adjusting. This is one data set, another data set using the same procedure, but completely randomizing the trials so that there is not an effect that you start with the easy ones and go down. It doesn't matter. They still are good at adjusting. They're not perfect, but they're pretty good considering that these guys don't do calculus. So that's that.
Thank you.
Yeah.
That's a happy note on which to end. Many thanks indeed.
Thank you very much.